Math 1314, Tyler Junior College, Section 1.5, Quadratic Equations, Video 10 of 10. Applications, a stealthy way of saying word problems. Disclosure. Most real-world word problems require, at a minimum, calculus, maybe trigonometry. The word problems you encounter in a college algebra class are usually bare bones, stripped down, simplistic, and as a consequence, sometimes not realistic. In order to handle real-world math, you need more powerful tools. Those tools are usually based in calculus. So I will be the first to say that most word problems in a college algebra class are cute, but not super realistic. Now this one I could argue is not that bad, but just wanted to give my opinion. A 16-foot by 24-foot swimming pool has a path around it. The path is of constant width. If the area of the path is 1,428 square feet, find the width of the path. I'm trying to think of a real-world scenario where this would be the setup. The only thing I can think of is you have a pre-existing swimming pool. You're going to put a concrete path around it. You have a fixed budget, so you know how much square footage you can afford, and then you want to figure out, okay, how big do I make this path? So I can concoct a situation, but it's precisely that. It's a concocted situation. So how do we even begin this? Well, there's a lot of strategies for solving word problems. One strategy is to draw a picture, and this is screaming to draw a picture because it's talking about a swimming pool. Now, I didn't say it was rectangular, and maybe I should stipulate that it's rectangular. The dimensions kind of suggest that it is, but we don't want to leave anything up to subjectivity. So we have this swimming pool that is 16 feet on one side and 24 feet on another. And I should stipulate that this path is adjacent to the swimming pool. So basically it looks like a picture frame. So you have this path going around the swimming pool, probably made of concrete. And what we're told is that it's the same width all the way around. So whichever side of the pool you're on, this is the same. And we're also told that the area of the path is 1,428 square feet. And the question is to find the width. So another strategy in word problems is to decide what you're looking for and give it a variable name. Since we're looking for the width, I think this is a good place to put an X. And because it's a constant width, I can put an X all over the place. So how are we going to find that width? Well, what do we know? We know the area of this path is 1,428 square feet. But how can we find the area of the path in terms of this picture? If you want to think of it as a picture frame, how can we find the area of the picture frame? Relative to the area that we do know, which areas do we know? Do we know this area? Not yet, but we could find it. If you remember that the area of a rectangle is length times width. So if we multiply 16 times 24, that'll give us the area of that. Do we know the area of this giant rectangle? Not just the path. But let's say I erased the rectangle in the middle and said, what's the area of the giant rectangle? Well, the formula for the area of a giant rectangle is still length times width. Maybe we can capitalize on that. The area of the path is the area of the larger rectangle minus the area of the smaller rectangle. And what we're trying to do is to set up an equation with the X so that we can solve for it. So maybe we can get there. Now we've already said that we could calculate the area of the smaller rectangle by multiplying 16 times 24. So we'll multiply that product in a moment and figure out that it's 196. Excuse me, except it's not. It's not 196, it's 384. Trying to show off. Fail. But what about the larger rectangle? What's the area of the larger rectangle? Well, in order to write the area of the larger rectangle, we would need something to represent its lengths and let's try that again. In order to find the area, or at least represent the area of the larger rectangle, we need expressions representing its length and width. In other words, we need something to write for that, and we need something to write for this. So what can we write for the length down here on the bottom? Is it 24? Well, no, 24 is just from here to here. It's missing these two pieces. But how long are these? They're both x. So the total length is 24 plus 2 of these x's. So 24 plus 2 of the x's is the total length of the big rectangle. What about the width of the big rectangle? Is it 16? No, 16 is just from here to here. We're missing this piece, which is an x, and this piece, which is also an x. So the width is 16 plus 2 of the x's. Well, now that we have an expression for the length and the width of the big rectangle, the larger rectangle, we can set up an expression for its area. Its length, 24 plus 2x, times its width, 16 plus 2x. I'm going to bring this 1428 down. We have an equation. Is it a quadratic equation? Will there be an x squared? When I FOIL this, there will be. So now that we have the equation, I think we can solve it. We need to start by multiplying. We need to start by getting this in general form. Ax squared plus bx plus c is equal to 0. These parentheses are in the way, so we need to bust it open. If we FOIL this, we'll get 24 times 16, which I think is 384, but it's not going to matter, as you're going to see in a moment, plus the inside is 2x times 16, plus the outside is 24 times 2x, and then plus the last part is 2x times 2x. I don't know why I'm going so slow through the FOIL process, but it's done. And then we still have this minus 16 times 24. Do you see why I no longer need to worry about what 16 times 24 is? Because whatever the answer is here is going to match this one, and these are going to cancel. So we have 1,428 is equal to, let's go find the x squareds. Here they are. 2x times 2x is 4x squared. And for our x terms, this is 32x, 2 times 16. This is 48x, so 32 plus 48 is 80. This is starting to look more like a quadratic equation. If we move the 1,428 to the right side, we get 0 equals 4x squared plus 80x minus 1,428. And now we have something we can start solving. I think I can solve it in space here. Let me move the equation over, and I'm going to switch sides. 4x squared plus 80x minus 1,428 is equal to 0. So how are we going to solve this? Quadratic formula, factoring? You can try either. I think we might use the quadratic formula because of the size of the numbers. But speaking of the numbers, here's a little suggestion when solving a quadratic equation. Before you jump into anything, look at the numbers and see if they have anything in common. All of these coefficients are even, so at the very least they're divisible by 2. But are they divisible by 4? Well, 80 will divide by 4, but will 1,428? A real quick check with the calculator says yes, it will. So when you're doing the quadratic formula, if you happen to notice that the coefficients have a common factor, what you can do prior to the quadratic formula is to divide both sides by that common factor. In this case, I can divide everything by 4. Technically, this would split into 3 fractions and each would reduce individually, but they will all reduce by 4. 4x squared divided by 4 is x squared. Positive 80x divided by 4 is positive 20x. And with a little calculator assist, or maybe even not, 1,428 divided by 4 is 300, I should probably just get out a calculator, 70, no. 357. Let me check that. Should just did it in the calculator in the first place. Saved a little bit of time. Yay, 357. At this point, you could try to factor or you could get out the quadratic formula. I choose the quadratic formula. I'm pretty sure that this is prime and won't factor. So the quadratic formula says x equals negative b, so negative 20, plus or minus the square root of b squared, so 20 squared, minus 4 times a, excuse me, 4 times a is 1, times c is negative 357. Negative 357. All over 2a, so all over 2 times 1. So x equals negative 20 plus or minus over 2. And let's just figure out the discriminant, the part under the square root. I know that's 400. 4 times 1 times 357. Well, it does, 1,428. I was like, where have I seen that number before? This divided by 4 was 357, so 357 times 4 should be that. The double minus makes it a positive, so the discriminant, the part under the square root, should end up being 1,828. I'm running out of room, so I'm going to have to get rid of something. I'll get rid of the picture. Now here's where things get a little bit different. If this were just an equation that we were solving, solve this, or even all the way up here, solve this, and absent of any context, the correct thing to do would be to start simplifying this completely. But if I'm building that swimming pool, well, the pool's already built. If I'm constructing the path around it, and somebody gives me an answer like this to tell me how wide the path is, I'd look at them like they're an idiot. I know what the width of the path is. What is it? Negative 20 plus or minus the square root of 1,828 all over 2. You're fired. How am I supposed to measure that out? When you're calculating a value in a word problem that is measuring or counting something, answers like this are completely useless. So we're going to get a decimal equivalent by putting this into a calculator. Now this represents two solutions. One solution is negative 20 plus the square root of 1,828 all over 2. And the other solution is negative 20 minus the square root of 1,828 all over 2. So all I have to do is put those in a calculator and see what I get. Except I'm not going to put both of them in. Why not? Because one of them can't possibly be the answer to how wide is the path. And it's the second one. And how can you tell? Both terms on top are negative. When I combine them, I'll get a bigger negative. When I divide it by half, by 2, it will still be negative. This answer, without even looking at a calculator, must be negative. And since we're measuring the width of a path, can't possibly be the solution. So I just have to figure out this one. And I've got a rinky-dink calculator here, but I think I can pull this off. Let's do 1,828 and square root it first. And then we're going to add negative 20, which is the same as subtracting 20. And then we're going to divide that answer by 2. So I get to we'll take it to one decimal place, 11.4 feet. But if you wanted to turn it into feet and inches, it would be 11 feet. So take off the 11 feet and multiply the rest by 12. It's about 11 feet and 4.5 inches. Let's do this, 11 feet, 4.5 inches. So yeah, applications can sometimes lead to something as simple as the quadratic formula, or excuse me, quadratic equations, which you can solve using the quadratic formula. But contextually, you should ask yourself, do your answers make sense? So a negative answer would not make sense. Don't get me wrong, excuse me. This is a solution to that equation, or any variation of it in between. But it's not a solution to the word problem, because the solution to the word problem had to be a positive answer.